Our own sun is a lonely island in the cosmic ocean. Now picture a sky dominated not by one star, but by seven. This is the reality inside a septuple star system, one of the rarest and most chaotic gravitational arrangements in the universe. We have uncovered 50 truly bizarre secrets about these celestial families, and you are about to explore them all. You will learn how planets might survive with 7 suns, and why some of these stars are engaged in a gravitational tug of war that defies physics. How can something so complex and violent exist for billions of years without tearing itself apart? The first strange discovery forces us to confront a reality of near impossible odds. Our galaxy contains hundreds of billions of stars, and most of them are not alone. Binary pairs and triple systems are the cosmic norm, but a stable family of 7 stars is something else entirely. Finding one is statistically equivalent to locating a single, predetermined grain of sand on every beach across our entire planet. Their very existence defied our early, simpler models of star formation. Astronomers once pictured stars condensing peacefully from isolated clouds of gas and dust. The discovery of septuples shattered that calm image. It points instead to stellar nurseries of incredible violence and dynamism, where dense clusters of young stars gravitationally bully each other, capturing and binding in a frantic dance that, against all odds, results in a perfect, balanced chaos. This chaos has a hidden architecture, a delicate structure that keeps 7 suns from a cosmic divorce. The second strange discovery reveals that most septuple systems are arranged like a set of celestial nesting dolls. At the heart of this arrangement is a tight binary pair, 2 stars locked in a frantic, intimate dance. This pair is itself orbited by another close binary, the 2 duos circling each other to form a stable quadruple system. And this entire complex family then swings around a distant triple system of stars, completing a gravitational ballet on an almost unimaginable scale. This intricate hierarchy is the secret to their survival. Without this specific layering of orbits within orbits, the gravitational forces would be too chaotic. The stars would play a game of cosmic pinball, eventually hurling each other into the void. Instead, the close pairs handle their own intense interactions, while the wider orbits allow the different groups to pass each other at a safe, stabilizing distance. It is a fragile, perfect balance between connection and separation, a dance of 7 partners that has continued for billions of years. This delicate dance of 7 stars begins in a cosmic cradle of stunning violence. The third strange discovery takes us to one of the youngest septuple systems ever found, a newborn stellar family still swaddled in the thick gas and dust of its nursery. Here, the chaotic process of multi-star birth is frozen in time, giving astronomers a front-row seat to a spectacle we once thought was pure theory. The environment is nothing short of tumultuous. Each of the infant stars is still surrounded by its own whirling disk of material, a potential birthplace for future planets. Thick tendrils of gas connect them like cosmic umbilical cords, and the space between them crackles with the energy of their violent gravitational interactions. Observing this system is like finding a photograph of your own family, not as you know them today, but from the very moment of your birth. It answers a fundamental question that has long puzzled scientists. Did all 7 of these stars form together in a single, catastrophic collapse of a giant gas cloud, a true family from the very start? Or were they separate individuals born in the same crowded neighborhood, only to be gravitationally captured by one another in a series of dramatic close encounters? The evidence from this young system strongly suggests they are true siblings. The stars share a common motion and are chemically identical, pointing to a single origin story. They were all born from the same incredibly dense pocket of material, a pocket so rich and so turbulent that it fragmented not into 1 or 2 stars, but into 7. This discovery paints a picture of star formation that is far more prolific and intensely dynamic than we ever dreamed. It suggests that the universe, in its most fertile regions, can manufacture entire complex systems in one single, glorious and chaotic event. The chaotic nursery of a newborn septuple system is a far cry from the settled, mature architecture of a system like New Scorpii. This famous celestial landmark, one of the first septuples ever identified, reveals a fourth strange discovery. The orbits here are not neat, circular paths but wild, roller coaster ellipses that push the limits of gravitational physics. Within its complex hierarchy, certain stars follow these highly elliptical paths. For most of their long orbit, they maintain a safe, respectful distance from their stellar partners, but then they reach the point of closest approach, the periastron. At this moment, the star plunges terrifyingly close to its neighbor. The peaceful cosmic dance becomes a near collision. The gravitational tides at this point are immense. They stretch and distort the very bodies of the stars, pulling atmospheres into vast, streaming arcs of superheated plasma. This can lead to mass transfer events where one star literally steals material from the other. A river of star stuff flows from one body to its companion, defying our simple predictions of how gravity should behave in a stable system. We are left to wonder how such a violent, intimate interaction can repeat for millions of years without the stars merging or being torn apart. This is not a placid celestial clockwork, it is a gravitational daredevil act performed on a cosmic stage. This stellar daredevil act leads to a fifth, even stranger discovery, a puzzle that challenges the very story of how stars are born. Within these septuple families, astronomers find stars that simply should not exist together. Picture a stellar giant, a brilliant blue O-type star, a cosmic titan that burns through its nuclear fuel in just a few million years. It lives fast and dies young in a spectacular supernova. Now, right alongside it, orbits a tiny, faint red dwarf, a stellar miser so frugal with its fuel that it can shine for trillions of years. According to our standard models, stars born from the same cloud of gas and dust should be like siblings from the same parents. They should share a similar chemical makeup and, crucially, be roughly the same age. They should have formed at the same time. Finding a massive, short-lived star and a diminutive, ancient one in the same gravitational embrace is like finding a newborn baby and a 1,000-year-old sage who are supposedly twins. It defies logic. How can two stars with such drastically different life expectancies be part of the same family? This bizarre coexistence forces astronomers to reconsider the process of star formation in these incredibly dense environments. Perhaps the original nebula was not a uniform soup of gas. It might have been a chaotic patchwork of pockets with wildly different densities and temperatures. One exceptionally dense knot collapsed to form the brilliant blue O star, while a much smaller, cooler fragment became the red dwarf. They were born as neighbors but never as true equals. This means a single stellar nursery can produce a complete demographic of stars all at once, from the brilliant, short-lived giants to the faint, eternal embers. The septuple system becomes a cosmic time capsule, preserving a snapshot of that initial, turbulent chaos, a family portrait featuring members at every possible stage of stellar life, all bound together by gravity. This frantic gravitational ballet sometimes produces a true rebel, a star that refuses to follow the rhythm. The sixth strange discovery focuses on a mysterious runaway star found within a septuple system. This particular star moves with a startling velocity, a speed so high it seems intent on escaping its own family. Its motion is an anomaly, a break from the shared, stately drift of its 6 siblings through the galaxy. How does one star acquire such a reckless speed while the others remain bound? Astronomers see 2 compelling and equally dramatic explanations. The first is an internal slingshot. Within the complex choreography of 7 stars, close encounters are inevitable. it is possible this runaway star once swung too close to the system's central binary or passed by the wider triple. Such a near miss would act like a gravitational catapult, transferring a tremendous amount of orbital energy into the star and flinging it outward at a breakneck pace. This would be a violent event, but one contained entirely within the family, a sibling argument with cosmic consequences. The second theory is even more profound. It suggests an intruder, a visitor from another star system that passed through this one millions of years ago. This foreign star could have gravitationally interacted with one member of the Septuple, stealing energy from it and leaving it with this unusually high velocity before continuing on its journey. This scenario paints the runaway not as a rebel, but as a victim of a long-forgotten celestial crime. Its speed is a permanent scar, evidence of a dynamical interaction that forever altered the system's delicate balance. Whether the cause was an internal slingshot or an external trespasser, the runaway star stands as a living record of past violence, a reminder that even the most stable-looking cosmic families have turbulent histories written in their motion. The runaway star's escape velocity is only part of the gravitational story. The seventh strange discovery uncovers vast, swirling disks of dust and rock encircling individual stars deep within these systems. These are not the smooth, primordial disks of a newborn star, but something far more telling: debris disks. They are the aftermath of cosmic construction, the leftover gravel and planetesimals from a violent period of planet formation. Finding such disks here is astonishing. It means that despite the gravitational turmoil of 6 other suns constantly tugging at the material, enough of it coalesced to attempt building worlds. This raises a breathtaking possibility. Planets might actually exist in a Septuple star system. How could a planet possibly find a stable orbit in such a gravitational madhouse? The answer lies in 2 extreme and equally bizarre scenarios. The first is a tight local orbit. Picture a planet not circling the entire system, but one specific binary pair at its heart. This world would orbit so close to its 2 parent stars that the gravitational influence of the other 5 distant stars becomes negligible, a faint background pull. On this planet, the sky would be a constant spectacle. 2 brilliant suns would dominate the heavens, perhaps so close they appear to touch, casting double shadows. The other 5 stars would shine as impossibly bright, permanent points of light, never rising or setting, but wheeling slowly across the sky in a complex, eternal dance. It is the ultimate Tatooine, a world with not 2 but 7 suns in its sky. The second possibility is at the opposite extreme, a planet on a grand, sweeping orbit around the entire Septuple system. This world would be so far out that the 7 stars appear as a single, tangled knot of light, a brilliant stellar nest at the center of its long, long year. Its orbit would have to be meticulously calculated, placed within a narrow band of gravitational stability where the combined pull of all 7 stars acts as a single central point. A slight deviation and the planet would be ejected into the void. The day-night cycle on such a world is difficult to even conceive. For most of its orbit, it would have a single, bright source of light in the sky, that clustered Septuple sun. But during rare alignments, as it swung past different pairs within the system, one of the other stars might briefly flare into a second, separate sun, creating a temporary and terrifying double noon. The very existence of these debris disks suggests that against all odds, in the calm eye of a 7-star hurricane, planets can and do form, offering the potential for the most alien skies in the entire galaxy. This stellar heartbeat reveals an even deeper layer of complexity within the 8th strange discovery. Astronomers have found a system where the core is not a simple binary, but a quintuple system, a family of 5 stars all orbiting each other in a dizzying arrangement. And within that tight-knit group of 5, 2 of the stars are what we call eclipsing binaries. This means that from our vantage point, these pairs of stars periodically pass in front of each other, causing their combined light to dim in a regular rhythm. But here, the rhythm is not a simple beat. It is a chaotic, overlapping symphony of shadows. As these two eclipsing pairs within the quintuple dance around each other, their individual dips in brightness overlap and interfere. One pair might begin to eclipse just as the other pair is halfway through its own dimming event. The resulting light curve, the graph of the system's brightness over time, looks like a frantic EKG, a heartbeat from a cosmic patient in a state of perpetual fibrillation. There are shallow dips, deep plunges, and complex stair-stepped patterns that repeat only after a very long and intricate cycle. Untangling this signal is one of the most demanding computational challenges in all of astronomy. It is like trying to isolate the individual voices of 5 people who are all talking at once, while also spinning around in a circle. Yet for those who can decipher it, this chaotic light curve is a scientific goldmine. Each specific dip and wiggle encodes incredibly precise information. The depth of a dimming reveals the exact size of a star relative to its partner. The timing and shape of the eclipse give away the star's orbital speeds and their precise temperatures. By meticulously modeling this chaotic heartbeat, astronomers can essentially weigh these stars with astonishing accuracy, determining their masses to within a single percentage point. This messy, overlapping signal provides a clearer picture of the stars themselves than we could ever get from studying a calm, solitary sun. The very chaos of the system becomes the key to unlocking its most fundamental secrets. These overlapping eclipses reveal stellar secrets, but the light from these stars holds an even stranger story. The 9th discovery uncovers bizarre chemical fingerprints within the atmospheres of certain stars in Septuple systems. Their light, when broken down into a spectrum, shows unusually strong signatures for heavy elements like barium and europium. This is a profound cosmic anomaly. You see, these particular elements are not forged in the calm nuclear furnaces of an average star. They are created in the most violent events in the universe, the titanic explosions of supernova. Finding them in such high concentrations in a living star is like finding fresh volcanic ash on a green, peaceful meadow. It is evidence of a cataclysm that happened right here in this very system. The scenario it paints is both dramatic and terrifying. Billions of years ago, one of the 7 stars, a massive sibling, must have reached the end of its short life. It did not go quietly. It exploded in a supernova of unimaginable force, blasting its newly forged heavy elements out in a searing, radioactive wind. This wave of stellar debris, rich in exotic materials, would have washed over the other 6 stars. Their outer atmospheres absorbed this cosmic pollution, permanently recording the event in their chemical DNA. The fact that the system still exists today is a miracle of celestial survival. A supernova explosion is so powerful it can easily dismantle a gravitational family, sending the surviving stars flying apart forever. That these 6 stars remained bound, that they withstood the blast and the sudden loss of 1/7 of their system's mass, means their orbital dance was robust enough to endure a stellar apocalypse. The stars we see today are living relics, their atmospheres scarred by the death of a sibling, a permanent memorial to a violence that failed to tear them apart. These chemical scars are a testament to a system's survival, but its gravitational landscape is a perpetual minefield. Discovery 10 takes us to the concept of Lagrange points, those famous gravitational sweet spots. Around a single star or even a stable binary, these are regions where the pull of gravity and the push of centrifugal force perfectly balance. An object placed there, like a satellite or an asteroid, can theoretically park itself in a stable orbit. It is a cosmic parking space, but in a septuple system, this elegant idea breaks down completely. The gravitational tug of war between 7 stars creates not a few stable points, but a constantly shifting, shimmering web of them. These are not peaceful havens, they are temporary traps in a chaotic gravitational field. astronomers have detected faint, shimmering clouds of dust and swarms of small asteroids caught within these unstable Lagrange points. For a time, these objects appear to have found a stable home, orbiting a point in empty space as the stars whirl around them. But the stability is an illusion, a fleeting moment in a much longer dance. The slightest shift in the positions of the other stars, a tiny nudge from a distant stellar partner, can utterly destroy the delicate balance. When that happens, the trapped particles are not gently nudged away. They are violently ejected, flung out of the Lagrange point at tremendous speeds. This process effectively turns the entire Septuple system into a natural particle accelerator. These regions do not gently guide objects, they act like cosmic slingshots, hurling rocks and dust out into the void or sometimes even inward, on a collision course with one of the stars. The entire system is surrounded by this invisible, dynamic network of gravitational whirlpools, each one offering a temporary refuge before inevitably spitting its contents back into the chaos. These chaotic gravitational tides are matched only by the invisible forces they unleash. The 11th strange discovery pulls back the curtain on the immense and tangled magnetic fields that envelop these systems. Each of the 7 stars constantly blows out a stream of charged particles, a stellar wind flowing from its surface at millions of kilometers per hour. In a solitary star, this wind expands outwards into a relatively calm bubble. But here, with 7 stellar gales blowing at once, the result is a perpetual collision of titanic forces. Where these winds slam into each other, they create violent shock fronts, cosmic sonic booms that heat the gas to incredible temperatures and compress the star's individual magnetic fields into a single, knotted web of immense power. These magnetic tangles are not passive structures. They act like the universe's most powerful particle accelerators. Charged particles, electrons and protons, become trapped in these twisting magnetic fields and are whipped back and forth, gaining speed with each pass until they are traveling at a significant fraction of the speed of light. This creates intense, flickering beacons of radio waves that astronomers can detect from across the galaxy. To stand within such a system, if it were possible, would be to experience a constant, silent storm of radiation and energy. The sky would shimmer with invisible, lethal forces, a web of power so dense it could tear matter apart at the atomic level. This makes Septuple systems unparalleled natural laboratories. They allow us to observe the same kinds of high-energy particle physics that we try to recreate in massive machines on Earth, but on a scale that is utterly impossible for us to build. The chaotic dance of 7 stars gives birth to a fleeting, violent environment where the fundamental laws that govern matter and energy are written large across the cosmos. These violent magnetic storms are not the only invisible energy these systems produce. The 12th strange discovery reveals that some Septuple systems are brilliant, unexpected beacons of X-ray radiation. This is deeply unusual. Your typical solitary star like our Sun is a relatively quiet source of X-rays, emitting only a faint trickle from its superheated outer atmosphere. For a star system to shine so brightly in this high-energy light, something extraordinary must be happening within its gravitational embrace. Astronomers see 2 primary and equally dramatic explanations for this intense X-ray glow. The first possibility involves the sheer stellar activity magnified by proximity. Many stars, especially young, rapidly spinning ones, have incredibly active and violent coronae. These are their outer atmospheres, regions of multimillion-degree plasma that can unleash powerful flares. In a Septuple system where stars often orbit very close to one another, the combined X-ray output from several of these hyperactive stellar atmospheres could be concentrated and amplified, creating a collective beacon far brighter than any single star could produce on its own. It would be like the difference between hearing a single firecracker and standing in the middle of a full-blown fireworks display. The second possibility is far more exotic and hints at a hidden, violent past. The X-rays might not be coming from ordinary stars at all. They could be generated by a process called accretion. Imagine one star in the system, perhaps a bloated giant, slowly losing its outer layers to a nearby companion. But this companion is no ordinary star. It is a compact, ultra-dense remnant, a white dwarf, or even a neutron star. As the stolen gas spirals down onto the surface of this incredibly dense object, it is compressed and heated to temperatures of millions of degrees, causing it to glow with intense X-rays. This scenario suggests a secret history for the system. It means that one of the original 7 stars has already died. It lived out its life and expired in a supernova, leaving behind this dense, dark ghost that now orbits silently with its siblings, only revealing its presence by siphoning material from a still-living partner and screaming its existence across the universe in pulses of high-energy light. This single, unseen point of X-ray emission forces us to reconsider the entire family tree of the system, implying a history of stellar death and rebirth woven into its complex dance. The very heartbeat of these systems is changing. Astronomers have made a 13th strange discovery, observing that the orbital periods of the stars, the rhythm of their celestial dance, is not constant. The clockwork of the heavens is running fast or slow. These are not random fluctuations, but precise, measurable shifts in timing. A binary pair that once eclipsed every 3.2 days might now do so every 3.2001 days. This minuscule change, accumulated over thousands of orbits, reveals a system in a state of continuous, dynamic evolution. The causes for this temporal drift are as profound as they are varied. One possibility is a silent river of star stuff flowing between 2 closely orbiting partners. If one star is siphoning mass onto its companion, the entire gravitational balance of their dance shifts. It is like 2 ice skaters holding hands and spinning. If one skater pulls the other inward, their spin accelerates. This transfer of mass alters the orbit, speeding it up or slowing it down in a predictable way. Another tantalizing possibility is the hidden hand of planets. An unseen, Jupiter-sized world orbiting far from the central stars would exert its own tiny gravitational tug, subtly pulling on the stars and causing their orbital timing to advance or retard slightly with each pass. But the most mind-bending explanation comes from the fabric of spacetime itself. Einstein's theory of general relativity predicts that massive objects in tight orbits will slowly precess, their point of closest approach gradually shifting over time. This effect, observed in the orbit of Mercury around our Sun, is magnified 1,000-fold in the intense gravity of a close septuple binary. Measuring these infinitesimal changes in a system of 7 stars provides the most extreme test of Einstein's theory we have ever devised. We are using the universe's most chaotic gravitational laboratories as a super-precise clock, listening for the tiny ticks and tocks that confirm our deepest understanding of reality, or perhaps one day reveal its first crack. The rhythmic wobble of a visible star betrays an unseen monster. This 14th discovery is perhaps the most chilling, the dark companion hypothesis. In one particular septuple system, astronomers have noticed something profoundly wrong with the motion of the 6 stars we can see. Their paths are not smooth, predictable ellipses. Instead, they show a distinct rhythmic wobble, as if they are all being gently tugged by an invisible hand. The mathematics is inescapable. This wobble reveals the gravitational signature of a 7th object, one with a mass several times greater than our own Sun, yet one that emits absolutely no light. It is a dark companion, a ghost in the celestial machine. The implications are staggering. An object this massive and this dark can only be one of 2 things. It could be a neutron star, the collapsed, ultra-dense core of a dead star, so compact that a single teaspoon of its material would weigh billions of tons. Or, even more incredibly, it could be a stellar mass black hole. This would be a black hole not at the center of a galaxy, but one hiding in plain sight within a family of living stars, a predator lurking in the cosmic shallows. Its presence is felt only through its gravity, a subtle distortion in the dance of its 6 bright siblings. How did such a terrifying object become part of this family? The most likely story is one of cosmic betrayal. Billions of years ago, this system had 7 bright stars. The most massive of them, a true behemoth, lived its short life and then died not with a whimper but with a catastrophic collapse. Its outer layers were blasted away in a supernova, but its core imploded with such force that it crushed itself into a singularity, a black hole. The incredible fact is that the supernova explosion was somehow asymmetrical, a cosmic kick that was not powerful enough to eject the newborn black hole from the system. It remained bound by gravity to the stars it once called siblings, now a dark, silent remnant of a violent past. This makes septuple systems unparalleled hunting grounds. Finding isolated stellar mass black holes is notoriously difficult, as they are, by their very nature, invisible. But here, the bright stars act as perfect tracers, their motion painting a clear picture of the invisible monster that walks among them. We are not just looking at a family of 7 sons, but at a cosmic crime scene where the murderer still lingers, hidden in the shadows cast by the living. This invisible monster leaves its mark not just on the stars, but on the very space between them. The 15th discovery reveals vast, ghostly streamers of gas and dust stretching away from a septuple system like the tendrils of a cosmic jellyfish. These are tidal tails, immense structures that act as a permanent record of the system's violent birth. They are the material that did not make it, the gas and dust that was stripped away during the frantic gravitational encounters of the system's infancy. When the 7 stars first formed and began their complex dance, their close passes acted like gravitational slingshots, not just on each other, but on the surrounding cocoon of primordial material. These close encounters pulled and stretched the leftover gas, shearing it off into long, flowing rivers that were then cast out into interstellar space. These tails are not static. They drift slowly away from the system over millions of years, fading as they disperse, but their composition holds a secret. By analyzing the specific light signatures from the gas in these tidal tails, astronomers can perform a kind of cosmic archaeology. They can determine the precise mix of hydrogen, helium, and trace heavy elements that were present in the original stellar nursery. This is like finding a fossilized footprint and being able to tell not just the size and weight of the creature that made it, but also what it had for breakfast on the day it left that impression. The tidal tail is a fossil of the cloud itself, a sample of the pristine material from which all 7 stars condensed. Finding that this material matches the chemical makeup of the stars themselves confirms they are true siblings, all born from the same single, massive reservoir of gas. These ethereal streamers, often invisible to the naked eye, are the ultimate evidence of the system's shared origin, a fading signature of the chaotic event that bound 7 suns together for life. These ghostly tidal tails are a fading echo of the system's birth, but the greatest puzzle is not how they began, but how they endured. The 16th strange discovery confronts us with a reality that seems to defy the laws of probability itself. These septuple systems are not just stable for a few million years. We observe them shining brightly, their complex dance intact after billions of years. This longevity is a statistical miracle. When astronomers run computer simulations modeling every possible gravitational interaction between 7 stars, the result is almost always the same: cosmic chaos. Most random arrangements of 7 massive bodies lead to a rapid and violent disintegration. Stars are ejected like pinballs, flung into the dark of interstellar space, while others spiral inward in catastrophic collisions. The fact that we can look up and see ancient, fully formed septuple systems means they are not random accidents. They represent a specific and incredibly rare solution to a 7-body gravitational problem. They must have been born with a very particular architecture, the precise orbital distances and angles that allow their gravitational influences to cancel out rather than amplify over eons. It is a level of fine-tuning that seems almost deliberate, as if the initial conditions of their stellar nursery were perfectly calibrated to create a lasting family. This delicate balance is so fragile that even a slight nudge during their infancy, a passing star from a neighboring system, could have thrown the entire arrangement into disarray. That it survived is a testament to a quiet corner of the galaxy, a peaceful cradle where this most complex of celestial clocks could be wound up and set in motion, ticking perfectly across the ages. This spectroscopic soup creates a puzzle of almost impossible complexity. When we point our telescopes at a septuple star system, the light from all 7 suns arrives blended into a single, tangled signal. We cannot simply look at one star at a time. Instead, we get a composite spectrum, a single rainbow of light where the unique chemical fingerprints of 7 different stars are overlaid, one on top of the other. Imagine trying to listen to a symphony orchestra, but instead of hearing the distinct sounds of violins, trumpets, and drums, you hear only one single muddled chord. Your task is to identify every instrument in the orchestra and even determine what note each one is playing from that one combined sound. This is the monumental challenge astronomers face. Each star in the system has its own temperature, its own gravity, and its own chemical composition. A hot blue giant star will imprint a very different pattern of dark and bright lines on the spectrum than a cool red dwarf. In this blended light, the strong hydrogen lines from one star might completely wash out the faint calcium lines from another. The subtle Doppler shifts that reveal a star's motion are blurred, making it nearly impossible to track the individual orbits within the central quintuple system. For decades, this spectroscopic confusion meant that the detailed properties of these stars remained locked away. We knew the system existed, but the intimate secrets of its individual members were hidden in plain sight. Unraveling this knot is now a frontier of modern data analysis. It requires advanced algorithms and machine learning techniques that can perform a kind of cosmic blind source separation. These computer models are trained on the spectra of hundreds of thousands of single stars. They learn to recognize the subtle patterns and then, like a master chef reverse engineering a complex recipe, they are set loose on the spectroscopic soup of a septuple system. The algorithm makes an initial guess, proposing a combination of 7 different stellar spectra that, when added together, might recreate the messy data we observe. It then iterates, making tiny adjustments over and over, millions of times, slowly disentangling the threads of light until it produces a clean, probable spectrum for each of the 7 individual stars. This process is not perfect. It is a statistical best guess, but it is a guess that is becoming more accurate every year. This computational revolution is allowing us to finally meet the stars of these systems as individuals, to understand their masses, their ages, and their life stories, pulling them one by one from a sea of blended starlight. The same tangled web of gravity that we see through our telescopes may one day be heard as a chorus. Our current gravitational wave observatories are deaf to the slow, rhythmic music of septuple systems. The mergers of black holes and neutron stars they detect are like sudden, violent crashes of cymbals in the cosmic symphony. But the dance of 7 stars is a different composition entirely, a piece played in a lower, more patient register over billions of years. Their orbital periods are not hours or days, but centuries or even millennia. This creates gravitational waves with wavelengths so long they are measured in millions of kilometers, far beyond the range of any Earth-based instrument. Yet the future promises a new way of listening. Planned space-based observatories with lasers strung between satellites millions of kilometers apart are designed to tune into this low-frequency hum of the universe. A septuple system would not produce a simple, clean tone. Its gravitational wave signal would be a complex, overlapping chord, a cacophony of 7 different frequencies all interfering with one another. The central binary would generate its own distinct hum, while the wider quadruple and triple orbits would add deeper, slower bass notes. The combined signal would be a unique fingerprint, a direct readout of the system's hidden architecture. By learning to decipher this cosmic chord, we could measure the masses of every single star with a precision that light alone can never provide. We would no longer be inferring their dance from a distant, blurry picture. We would be feeling the vibrations of their motion ripple through the fabric of space-time itself, hearing the true rhythm of a celestial family that has been waltzing together since the dawn of time. The sky above this world is a canvas of pure celestial chaos. Instead of a single sun, its horizon is dotted with multiple orbs of fire, each a different hue in a cosmic artist's palette. A brilliant blue-white giant hangs near the zenith, its harsh, sharp light casting deep black shadows. Lower in the sky, a softer orange sun shares the heavens with a faint crimson-red dwarf, painting the clouds in washes of peach and rose. Their movements are not the simple arc of our sun. They trace complex, interweaving paths, a slow-motion ballet of light and color. Daybreak is not a single event, but a drawn-out symphony. First, the red dwarf might crest the horizon, bathing the landscape in a dim, twilight glow of deep red. An hour later, the orange sun rises, strengthening the light to a warm, earthly daylight. Finally, the blue star appears, flooding the world with its intense actinic glare. The process reverses in the evening, a protracted sunset that can last for hours, with colors shifting from blue to orange to a long, lingering red twilight. There are times when all 7 suns are above the horizon, creating a period of perpetual, multi-directional daylight. Shadows become a tangled mess, stretching and shrinking in conflicting directions, as if the very world is confused about the time of day. At other moments, a single sun might dip below the horizon, only for another to rise moments later, creating a false dawn in the middle of the night. The concept of midnight is meaningless here, replaced by an eternal, shifting interplay of light and color, a spectacle of such overwhelming beauty and strangeness that it would forever redefine the very idea of a sky. This septuple system may not be the end of its own story, but the violent beginning of another. These 7 suns could act as cosmic engines of creation, triggering the birth of entirely new stars around them. The process begins with the system's most massive members. Brilliant blue giants and O-type stars burn with a ferocious intensity, flooding their surroundings with an immense pressure of ultraviolet radiation. This radiation is a physical force, a relentless wind that slams into the surrounding, dormant clouds of gas and dust left over from the system's own birth. It does not gently push this material away, it sculpts and compresses it. The radiation strips electrons from atoms, creating shock fronts that travel through the nebulae like sonic booms. These shock waves squeeze the gas, increasing its density in specific, isolated pockets. Imagine a powerful gust of wind blowing across a field of dandelions. It does not simply scatter all the seeds, it can sometimes pack them tightly into the cracks of a fence post. In the same way, the shock waves from the septuple system can crush vast, tenuous clouds into dense, gravitationally unstable knots. When the density in one of these knots crosses a critical threshold, its own self-gravity takes over. The knot can no longer support itself against the collapse, and it begins to fall inward, igniting the nuclear furnace at its core and giving birth to a brand new star. This new star is a second-generation descendant, its formation directly initiated by the violent existence of its 7 stellar parents. We then see a remarkable family tree emerge. The original septuple system becomes the gravitational and radiative patriarch of a small, extended stellar cluster. It sits at the heart of a growing family of younger stars, all of them indebted to the initial chaos of the 7 suns. This paints a profoundly different picture of stellar ecology. A septuple system is not an isolated oddity, a cosmic hermit. It is a vibrant, active hub, a factory that uses its own immense power to seed its celestial neighborhood with new life, ensuring its gravitational legacy extends far beyond the dance of its original 7 members. The heart of the system remains a blur of light, a brilliant pinprick that refuses to reveal its secrets. Our most powerful telescopes strain to see it, but the core of this septuple family is simply too far away and its members too close together. We know from the frantic wobble in the light of the outer stars and the complex rhythm of eclipses that there is not one star at the center, but a tight-knit binary or even a triple system locked in a dizzyingly fast orbit. Yet to our eyes they appear as one. This unresolved core is the ultimate tease, a gravitational signature without a face. All the most dramatic action, the violent tidal pulls, the potential mass transfer, and the most intense magnetic fields are almost certainly happening right there in that unresolved point. It is like hearing the roar of a crowd from a sealed stadium. You know an incredible event is unfolding inside. You can feel the vibration through the walls, but you cannot see the players or the game. Our only window into this hidden realm is through the art of spectroscopy. As the stars in the core whip around each other, one periodically moves toward us while the other moves away. This motion imprints a subtle, shifting signature on their combined light, a Doppler shift that alternately stretches and compresses the light waves. In the spectrum, the dark absorption lines from each star split and merge in a complex, rhythmic dance. From this dance, we can calculate their orbital speeds, their masses, and even estimate their separation. We know they are terrifyingly close, perhaps completing an entire orbit in a matter of days. But we cannot see their individual surfaces, their flares, or the vast bridges of plasma that might be flowing between them. The unresolved core represents the final frontier within the system itself, a reminder that even as we unravel the grand architecture of 7 suns, the most intimate and violent interactions remain shrouded in brilliant, frustrating light, compelling us to build ever better eyes to finally peer into the storm. The path of this 7-star family across the galaxy holds a secret written in its motion. While the system glides through the void as a single unit, 1 or 2 of its suns are not quite keeping perfect pace. Their trajectory across the sky, what astronomers call their proper motion, is slightly but measurably different from the rest of the family. This tiny mismatch is a profound clue, a cosmic smudge on the system's birth certificate. It suggests that not all 7 stars are true siblings born from the same cloud. Instead, 1 or 2 of them might be adopted. Billions of years ago, when the original 5 or 6 stars were settling into their complex dance, their gravitational pull may have been strong enough to ensnare a passing vagabond star. This was not a gentle capture. It would have been a violent gravitational encounter, a celestial heist where the system stole a sun from a neighboring cluster or from the general field of the galaxy. The captured star, once a solitary traveler, was pulled into the chaotic dance, its path forever altered to conform to the rhythm of its new family. This solves one chemical mystery, explaining why a particular star might have a slightly different composition or age than the others. But it creates a new dynamical puzzle. For the capture to have been successful, the conditions had to be perfect. The passing star had to have just the right speed and approach angle. Too fast and it would have simply slingshotted away, too slow and it might have caused a destabilizing collision. That this delicate gravitational surgery was performed successfully and that the system remained stable afterward is a testament to both the system's powerful gravity and an incredible stroke of cosmic luck. The family we see today is not a pristine, original set but a blended one, its history written in the faint, divergent paths of its constituent stars. The architecture of these 7 suns is written in the rings of cosmic dust that orbit them. Discovery 23 reveals 2 distinct types of these construction zones, each telling a different story of creation and theft. Some stars possess their own private circumstellar disks, a personal reservoir of dust and rock held in a tight, possessive grip. These are the feeding zones for planets that would belong to one star alone, a world with a single parent in a sky filled with 6 other suns. The presence of these private disks is a testament to gravitational selfishness. It means that despite the constant gravitational tugging from its 6 siblings, this particular star was able to hold onto its own construction material, carving out a small, stable pocket of space where the rules of a single star system still apply. The material in these disks is often richer in heavier, rocky elements, having been baked by the intense heat of their solitary host star, a perfect recipe for forging terrestrial, Earth-like worlds. In stark contrast, other disks in the system are not private property but shared territory. These are the vast circumbinary disks swirling around not one but a pair of stars at the system's heart. Imagine a colossal, flat ring of gas and dust, so wide that a tight binary pair orbits within its central hole, like 2 dancers spinning on a vast, dusty stage. This shared environment is far more chaotic. The gravitational pull from 2 central stars creates shifting tides within the disk, stirring the material and creating regions of extreme pressure and density. Here, the feeding zones are not for small, rocky planets, but for gas giants. The vast scale of these circumbinary disks provides the sheer volume of raw material needed to build a Jupiter, while the complex gravity can trigger the rapid collapse that forms a giant planet's core. The very existence of these 2 disk types reveals a system-wide struggle for resources. A circumstellar disk around one star might show a sharp, truncated edge, its outer material visibly stripped away, stolen by the gravitational pull of a passing stellar partner. Meanwhile, a circumbinary disk might appear lopsided, its material piled up on one side by the rhythmic, double gravity of its twin suns. These disks are not just potential planetary cradles, they are active battlegrounds, their shapes and compositions a permanent record of the endless gravitational arguments between 7 hungry suns. The chaotic energy of these 7 suns sometimes erupts in perfect, terrifying unison. Discovery 24 reveals a phenomenon that defies simple chance, stellar flare activity that appears synchronized across multiple stars. On a normal star, a flare is a local event, a sudden and violent reconnection of magnetic field lines on its surface that unleashes a torrent of radiation. In a septuple system, these eruptions should be random and independent, like separate volcanoes on different continents. Yet observations show something profoundly different. 2, or sometimes even 3, of the stars will unleash a massive flare within hours of each other, a coordinated burst of violence that lights up the system. The probability of this happening by pure coincidence is astronomically low. It points to a deep, physical connection between the stars that transcends the simple pull of gravity. One compelling explanation lies in their tangled magnetic fields. We know these fields can form a vast, invisible web linking the stars. A major flare on one star could send a shockwave of energized particles racing along these magnetic highways. When this tsunami of plasma and energy slams into a neighboring star, it could act as a trigger, destabilizing that star's own magnetic field and forcing it to release its pent-up energy in a sympathetic flare. It is a celestial domino effect where one stellar tantrum directly incites another. The other possibility involves the relentless pull of tides. As stars in a close binary pair swing around each other, their gravitational pull constantly flexes and distorts their partners' interiors. This tidal squeezing can stir up the churning plasma deep within a star, amplifying its magnetic dynamo. When both stars in a pair reach the most stressful point of their orbit simultaneously, their internal dynamos could be pushed past a breaking point at the same moment, resulting in a synchronized flare from both. This synchronization means we cannot understand these stars as isolated entities. Their most violent outbursts are a collective behavior, a stellar conversation written in fire. They are a single, interconnected organism where a disturbance in one part sends a ripple through the whole. forcing the entire family to flare up in a shared, brilliant, and deadly protest against the bonds that hold them together. The most massive stars in these families live lives of extravagant waste. They burn through their nuclear fuel at a ferocious rate, and in return, they blast their own outer layers into space. This is not a gentle evaporation, but a hurricane of particles streaming outward at millions of kilometers per hour, a stellar wind of unimaginable power. In a solitary star, this lost mass simply dissipates into the void, a silent and final farewell. But here, with 6 other suns as neighbors, nothing ever truly leaves. This ejected material becomes a new player in the gravitational dance. The stellar wind from a blue giant does not drift away peacefully. It slams into the calm stellar winds of its cooler, smaller siblings, creating violent shock fronts that heat the gas until it glows with a faint, eerie light. This can weave a complex common envelope of gas, a thin, shimmering atmosphere shared by multiple stars, turning the space between them into a visible, nebulous fog. In rarer, more dramatic cases, the captured wind can wrap around a neighboring star like a cosmic cloak. If the receiving star is a compact, dense object like a white dwarf or neutron star, this stolen material doesn't just cloak it, it spirals down onto its surface in a furious accretion disk powering brilliant X-ray flares. This continuous theft of star stuff has a slow but inevitable consequence. Every time a massive star exhales a breath of stellar wind, it loses a tiny fraction of its mass. Since gravity is a direct result of mass, the star's gravitational pull weakens ever so slightly. Think of it as a dancer in a spinning circle who is gradually becoming lighter. Their grip on their partners loosens. This microscopic change, repeated over millions of years, forces the entire system to adjust. Orbits must widen, periods must lengthen. The delicate clockwork of the Septuple system is constantly being rewound by its own most profligate members. The system we see today is not the system as it was born, nor as it will be a million years from now. It is a living, breathing entity, its shape slowly evolving as its largest stars bleed themselves into the shared space, forever altering the music of their own celestial dance. The very age of these stellar families is a mystery written in conflicting data. Astronomers possess several powerful clocks to date a star system, but in a septuple, each one tells a different time. The first method relies on stellar evolution models. By measuring a star's color and brightness, we can place it on a chart that traces its life from birth to death. A hot blue star is clearly a vibrant youth, while a cooler red giant is in its old age. In a well-behaved system, all the stars should point to roughly the same age. But here, the story falls apart. One star might appear to be a sprightly 50 million years old, while its immediate gravitational partner shows all the signs of a venerable 2 billion years. It is like finding a toddler and a senior citizen who claim to be identical twins. The second method, kinematic tracing, adds to the confusion. This technique tracks the system's motion backward through the galaxy, using the known paths of nearby star clusters as a cosmic map to trace its origin. This often points to an age far older than any of the individual stars seem to be. How can the family be older than its own members? This glaring discrepancy is a clue to a deeply turbulent past. It strongly suggests that these 7 stars are not all true siblings from a single, cohesive birth event. Instead, the system we see today might be a blended family, the product of a long and dramatic history. The most likely scenario is one of galactic capture. Perhaps a smaller, younger cluster of stars, born only 50 million years ago, drifted too close to a much older, stable quintuple system. A delicate gravitational dance ensued, resulting in the older system capturing 2 of the younger cluster's stars, pulling them into its complex orbit. The original quintuple brings its ancient age to the family, while the 2 captured newcomers contribute their youthful vigor. The different dating methods are not broken, they are simply reading different chapters of the same epic story. The stellar evolution clock tells the age of the individual stars, while the kinematic clock reveals the age of the gravitational family itself. This age puzzle forces us to see these systems not as static monuments, but as dynamic entities that can grow and change over billions of years, acquiring new members and rewriting their own histories through gravitational encounters. This ultimate fate hangs over the Septuple system like a dormant curse. We know one of the massive stars is destined to explode, its life ending in a supernova of unimaginable violence. The initial blast would be catastrophic, a shockwave of energy and a hail of high-energy particles slamming into its 6 siblings. But the true danger lies not in the flash but in the aftermath. The supernova would instantly remove a significant fraction of the system's total mass, fundamentally weakening the gravitational glue that holds the family together. Orbits would become unstable, potentially flinging 1 or 2 stars into the void. Yet there is a more terrifying, cascading possibility. Imagine the supernova leaves behind a dense, spinning corpse, a neutron star. This remnant, now a fraction of its original size, would still hold immense gravity. If it orbits very close to a stellar partner, the scene is set for a slow-motion disaster. The neutron star would begin to siphon material from its living companion. This stolen gas spirals down onto the neutron star's surface, accumulating over thousands of years. With each passing millennium, the pressure and heat at the base of this growing layer of stolen star stuff increases exponentially. Eventually, it crosses a critical threshold. The entire accumulated mass erupts in a runaway nuclear fusion reaction, detonating in a titanic thermonuclear explosion. This is not the core collapse supernova of a massive star, but a different kind of blast, one that can happen again and again on the same object. This single neutron star could become a repeating bomb, erupting every time it steals enough material from its neighbor, but the chain reaction could spread. The shockwave from one of these explosions could violently compress the core of another massive star in the system, one that was already on the verge of collapse. This external push could be the final trigger, forcing that second star to go supernova prematurely. Its death would then create another dense remnant, potentially starting the entire grisly process over again. A septuple system could, in theory, experience not one, but a series of stellar apocalypses, a chain reaction of deaths echoing across millennia until the once brilliant family is reduced to a dark and silent collection of stellar ghosts, their gravitational bonds finally broken by the very violence they spawn. These gravitational niches could become the permanent homes for entire worlds. The 28th discovery explores the existence of Trojan asteroids and planets, objects that do not orbit a star directly, but instead share its orbit. In a simple 2-body system, there are 5 Lagrange points where gravity balances. 2 of these, known as Trojan points, lie 60 degrees ahead of and behind the smaller body in its path. We see this in our own solar system, with swarms of asteroids sharing Jupiter's orbit around the Sun. But within a family of 7 suns, this elegant concept is stretched to its absolute limit. Here, the Trojan points are not stable parking spots, they are fractal and chaotic. A planet could theoretically occupy a Trojan point relative to one binary pair, while that entire pair itself is in a Trojan configuration with a wider triple star. It is a set of cosmic nesting dolls where each layer of the hierarchy has its own set of gravitational sweet spots. The result is a dizzying array of possible orbits, a labyrinth of stability within the overarching chaos. Advanced computer simulations reveal that against all odds, a few of these niches might remain stable for billions of years. Within them, you could find a world that is perpetually locked in a gravitational resonance with not one but several suns. The sky from such a Trojan planet would be a geometric marvel. It would always maintain the same position relative to its parent stars, like a celestial follower. If it trails 60 degrees behind a brilliant binary pair, those two suns would forever appear as a single, intensely bright beacon fixed in the sky, never rising or setting. The other stars in the system would wheel around this fixed point in a complex, predictable dance. The light and heat on this world would be constant, but its sources would be multiple and unmoving, creating a permanent, multi-directional twilight or an eternal, fractured noon. The existence of such a world is a testament to the hidden order within apparent chaos, a place where the relentless pull of seven suns finds a perfect, if temporary, balance, offering a refuge for a world that is forever a guest in the orbit of giants. A faint, unexpected warmth radiates from the heart of the system, a thermal whisper that visible light cannot see. Astronomers detect an infrared excess, a glow of heat that far exceeds what the seven stars alone should produce. This persistent warmth points to the presence of vast amounts of dust, but its signature tells a strange and violent story. The dust is not where it should be. It isn't confined to the neat, cold rings of a typical debris disk at the system's edge. Instead, this dust is warm, scattered, and located disturbingly close to the stars themselves, bathing the inner gravitational realm in a diffuse, heat-bathed haze. Such warm dust should not last long in this environment. The intense stellar radiation and gravitational tides should either blow it away like cosmic dandelion seeds or drag it down into the stars within a few thousand years. The fact that we see it at all means we are witnessing something recent and catastrophic. This is not the gentle leftover gravel of planet formation. It is the fresh, hot wreckage of a cosmic crash. The most compelling explanation is a recent collision of staggering scale. Imagine two protoplanets, each the size of Mars or even larger, on unstable orbits dictated by the chaotic gravity of seven suns. Their paths cross and they slam together not with a gentle merge, but with world-shattering violence. The impact vaporizes rock and metal, spraying a cloud of incandescent, molten droplets and fine dust throughout the inner system. This ejected material, still glowing from the heat of its own creation, creates the mysterious infrared glow we detect. It is the thermal echo of an apocalyptic event, a glimpse of a planetary system being born through sheer destruction. There is, however, an even more exotic possibility. This persistent warmth could be the faint body heat of a hidden, failed star. A brown dwarf, an object too massive to be a planet but too small to ignite sustained fusion, could be lurking within the dance. This cool, substellar object would be nearly invisible in optical light, but it would glow with a deep, intrinsic infrared warmth. Its gravitational presence could be the very thing stirring up the orbits of planetesimals, causing the very collisions that create the dust we see. So the infrared excess becomes a cosmic detective story. Is it the aftermath of a single titanic collision, a rare and fleeting snapshot of planetary chaos? Or is it the steady, warm breath of a dark, hidden giant, a shadowy eighth member of the family that has evaded our notice until now? This thermal mystery reminds us that even the light we cannot see holds the secrets to the most violent and formative processes unfolding within this stellar family. This stellar cannibalism unfolds as a slow-motion cosmic feast. Deep within the gravitational tangle of a septuple system, a pair of stars orbit so closely that their fates are irrevocably intertwined. One star, having aged and swollen into a giant, finds its outer atmosphere straying perilously close to its companion's gravitational grasp. The stronger, denser star begins to siphon this material away, pulling a river of superheated hydrogen from its partner in a process that can last for thousands of years. This is not a gentle transfer, it is a violent act of stellar theft. The stolen gas spirals down onto the predatory star, often forming a brilliant, hot disk of accretion that glows with intense light. Meanwhile, the donor star is left brutally exposed. Its lush, hydrogen-rich envelope is peeled away, layer by layer, until only its bare, helium-burning core remains. What was once a typical star is transformed into a bizarre, ultra-hot object known as a wolf-rayet star, a stellar corpse that shines with a searing, bluish-white light and is wreathed in tempestuous winds of its own stripped material. This metamorphosis would take billions of years in isolation if it happened at all. But in the crowded, dynamic environment of a septuple system, the process is dramatically accelerated. The gravitational nudges from the other 5 stars constantly perturb the binary pair, tightening their orbit and forcing them into an ever more intimate and destructive dance. The same chaos that threatens to tear the system apart also provides the precise conditions for this rapid stellar evolution, creating stellar vampires and their victims in a celestial drama that plays out over mere cosmic moments. This wild ride is not confined to their own gravitational dance. The 31st discovery pulls our view back to a truly cosmic scale, revealing that the entire septuple system is on a roller coaster path around the galaxy itself. Unlike our Sun's relatively circular journey through the Milky Way, some of these stellar families follow a wildly elongated, eccentric orbit. For billions of years, they have been plunging from the bright, crowded plane of the galactic disk out into the lonely, dark halo and then swinging back in again. This is not a leisurely tour, it is a cycle of extreme environmental change. When the system is in the dense galactic disk, it is surrounded by the gravitational pull of countless neighboring stars and giant molecular clouds. This constant, shifting pressure acts like a cosmic massage, potentially tightening the orbits of the inner stars and shaking loose any fragile planetary construction. Then the system swings out into the halo, a vast, empty realm where the gravitational tides relax and the background radiation drops to a whisper. Here, the system exists in profound isolation, its internal dynamics the only thing that matters for millions of years. This cyclic journey may have been the key to its survival. The periodic gravitational squeezing in the disk could have weeded out unstable configurations long ago, ejecting any stars that could not handle the pressure. Only the most robust and finely tuned gravitational dance, one that could withstand both the chaotic crowds and the deep silence, would have endured to the present day. The system we see now might be the hardened survivor of a much more violent past, its unique path around the galaxy acting as a crucible that forged its enduring, chaotic beauty. A faint, ghostly signature flickers within the rainbow of starlight, a set of spectral lines that simply do not belong. These are not the familiar marks of hydrogen or helium, but a mysterious barcode of dark and bright lines that appears only occasionally in the light from a septuple system before vanishing again. Astronomers have no clear match for them in their vast databases of atomic and molecular fingerprints. The first possibility is as profound as it is exotic. These lines could be the signature of a rare earth element or a heavy metal forged only in the hearts of the most massive stars, a substance so uncommon it is scarcely found anywhere else in the galaxy. These elements, when blasted into space by a supernova, would normally be diluted into the vastness of the interstellar medium. But here, locked within the gravitational walls of the septuple system, this enriched material could have been captured and concentrated, creating localized pockets of bizarre chemistry. The second theory points to unique molecules. The space between the 7 stars is a turbulent environment filled with radiation and shock waves. This could be a crucible for forming strange, transient molecules that are impossible to create under normal conditions, complex chains of atoms that briefly come together in these high-energy laboratories before being torn apart again. But the most tantalizing explanation involves the element technetium. This is a true atomic rebel, an element with no stable isotopes. Every form of it is radioactive, decaying into other elements in a matter of years or millennia. Finding technetium in a star's atmosphere is like finding a still smoking gun at a crime scene. It means a nuclear process must have created it very recently, right on the surface of the star itself. This points to a phenomenon called the S process, where neutrons are slowly captured by atomic nuclei deep within a star and then dredged up to the surface by powerful convection currents. The sporadic appearance of these lines suggests this is not a steady process, but a violent, episodic one. A star might undergo a convulsive internal mixing event, belching a cloud of freshly minted radioactive technetium into its outer layers, where it imprints its fleeting signature on the starlight for a few short years before it decays away into nothingness. This spectral ghost is a direct message from the heart of a star, a declaration that the nuclear fires within are still stirring, still creating, and still defying our expectations. This subtle drag is the universe's own form of friction, a gravitational brake applied not by touch but by influence. As a massive star plows through the crowded system, its immense gravity pulls on everything around it. It doesn't just attract other stars directly, it leaves a wake behind it, a trailing region of space that is slightly denser with the gravitational pull of all the material it has disturbed. Think of a giant ship moving through the ocean. The water parts before the bow, but it piles up into a large, churning wake behind the stern. Now imagine that the water itself is pulling back on the ship, creating a drag that slowly robs it of speed. In a septuple system, the ocean is the gravitational field created by the other 6 stars and all the dust and debris between them. This phenomenon, called dynamical friction, means the most massive stars are constantly swimming upstream against their own gravitational wake. The effect is incredibly subtle, acting over millions of years, but it is relentless. It gently steals orbital energy from the heaviest members of the family. This has 2 profound consequences for the system's architecture. First, the wildly elliptical, daredevil orbits we see today are slowly being sanded down. The dynamical friction smooths out the extremes, gradually circularizing the paths of the stars. The terrifyingly close periastron passes become less extreme, the gravitational tides less violent. The system is ever so slowly calming down. Second, and more dramatically, the massive stars begin to sink. As they lose orbital energy, they can no longer maintain their wide paths. They drift inexorably inward, migrating toward the gravitational center of the entire family. The system's core, already a tangled knot of stars, becomes even denser, packed with the heaviest members. This sinking process fundamentally rewrites the system's hierarchy over cosmic time, drawing the most powerful players into the most intimate and dangerous dance, setting the stage for future cataclysms. Deep within the gravitational whirlpool of a septuple system, a perfect cosmic clock could be ticking. The 34th strange discovery speculates on the existence of a pulsar hidden among the 7 suns. A pulsar is the collapsed core of a dead star, a neutron star spinning hundreds of times every second. As it rotates, it beams out a lighthouse-like pulse of radio waves with a rhythm more precise than any atomic clock built on Earth. If one of these stellar corpses is present in the system, its steady pulse would become our most powerful tool for mapping the invisible. Each time the pulsar moves in its orbit, swinging toward us and then away, the timing of its pulses would be minutely distorted. As it moves toward us, the pulses would arrive ever so slightly early, compressed by its motion. As it swings away, they would be delayed, stretched out. These are not simple delays. The pulsar would be weaving through the combined gravitational field of 6 other massive stars, each one tugging at it from a different direction. The resulting pattern in its pulse timing would be a fantastically complex record of every single gravitational hill and valley it traverses. It would be like dropping a sensitive microphone into a stormy sea and using only the sound of the waves to map the shape of every underwater mountain and trench. This data would allow us to weigh every star in the system with unparalleled accuracy, revealing hidden brown dwarfs or even silently orbiting black holes that other methods have missed. Most importantly, it would test Einstein's theory of general relativity under conditions of extreme gravity that we can never recreate. The pulsar's clockwork rhythm would feel the subtle drag of spacetime itself curving around its massive companions, its pulses advancing or retarding in ways that could either confirm our deepest theories of gravity or finally reveal where they begin to fray. This silent, spinning relic would transform the entire chaotic system into the universe's most grand and precise laboratory. These shifting shadows offer a fleeting glimpse into a hidden architecture. From our distant viewpoint, the disks of dust and gas encircling the stars do not just glow, they also cast darkness. As they orbit, one disk can pass directly in front of another, eclipsing its light and throwing a complex, moving shadow across the system. This is not a simple dimming, but a celestial shadow play on a billion-kilometer stage. Astronomers watch these events unfold like a slow-motion puppet show, and the shapes of the shadows tell a profound story. A sharp, clean silhouette might reveal a disk that is razor-thin and perfectly flat, a calm construction zone, but more often the shadows are distorted and warped. They stretch into long, graceful spirals or show deep, jagged gaps. These are the scars left by a life lived in a crowd. The gravitational pull from a passing star acts like an invisible hand, reaching in and stirring the disk, sculpting its material into these intricate patterns. A spiral arm in the shadow might trace the path of a stellar sibling that swung by 1,000,000 years ago, its gravity still imprinted on the dust. A dark gap in the silhouette could be the calling card of an unseen planet, its own gravity clearing a path through the debris as it orbits. By meticulously tracking how these shadows change and move, astronomers can perform a kind of cosmic tomography. They can build a three-dimensional map of the disks, understanding not just their shape, but their tilt, their thickness, and their texture. This dynamic silhouette is a real-time record of the system's gravitational arguments, a visible history of pushes and pulls written in shifting darkness against a backdrop of brilliant light. A star is missing from the family portrait. This is the hypervelocity escapee scenario, a theory that explains how a young septuple system might have violently purged one of its own. In the system's chaotic infancy, the gravitational dance was far more frantic and less stable than it is today. During one particularly close encounter, 3 or more stars could have swung around each other in a cosmic crack-the-whip maneuver. In this gravitational slingshot, one star absorbs the orbital energy of the others, accelerating to such an incredible speed that it breaks free from the system's grip entirely. It would not drift away, it would be catapulted out, reaching velocities of over 1,000,000 miles per hour, fast enough to escape the Milky Way itself. This star would then become a hypervelocity runaway, a lone wanderer on an eternal journey through the intergalactic void, its origin story written in its impossible speed. Back in the Septuple system, the remaining 6 stars would bear the permanent scars of this stellar divorce. The event would have been a profound shock to the system, literally. The sudden, violent loss of 1/7 of the system's mass would have sent a gravitational tremor through the entire family. Orbits that were once circular became stretched and eccentric. The stable hierarchy of the system was permanently altered, forced to find a new, shaky equilibrium after the traumatic ejection. The paths the 6 stars follow today are not their original paths, they are the evidence of this ancient catastrophe. Their unusual orbital angles and eccentricities are the lingering echoes of a day, billions of years ago, when their family was torn apart by its own internal chaos. This means that some of the 6 star systems we observe today may not have been born that way. They could be the survivors of a more violent 7-star past, their current stability a hard-won peace after a foundational act of cosmic betrayal. The stars themselves carry a chemical scar, a missing piece that points to a hidden history. Deep within the atmospheres of certain stars in these systems, astronomers find a profound lack of lithium. This element is the cosmic equivalent of a delicate flower, easily torn apart and consumed in the hot cores of stars. Yet its absence is not uniform across all 7 suns. Some stars are almost completely depleted, their lithium reserves utterly destroyed, while their immediate gravitational partners show perfectly normal, pristine levels. This patchy depletion is a chemical mystery written across the family. How can siblings from the same nursery show such different internal histories? One possibility lies in the star's infancy. Perhaps they did not all ignite their nuclear fires at the exact same moment. A star that formed just a few 100,000 years earlier than its siblings would have had that much more time to burn through its fragile lithium supply in its deep, churning interior. Their different depletion levels would then be a fossil clock, revealing the subtle age differences in their birth order. Another explanation dives into the star's internal dynamics. Stars are not static balls of gas, they are churning, convective ovens. Some stars may simply have more violent internal currents, dredging material from their deep, hot cores up to the surface where the lithium is destroyed, while other, calmer stars keep their lithium safely sequestered in their outer layers. But the most intriguing idea involves celestial pollution, but of a very specific kind. One star, perhaps a massive, windy giant, could be blowing its own lithium-depleted atmosphere out into the system. This material, rich in other elements but scrubbed clean of lithium, could then fall like a gentle rain onto the surface of a neighboring star, artificially lowering its measured lithium abundance and creating the illusion of depletion. This chemical fingerprint forces us to see these stars not just as gravitational partners, but as individuals with unique internal lives and histories, their atmospheres recording a story of formation, mixing, and influence that we are only just beginning to read. This ultimate gravitational embrace is the final act for the tightest binary pairs. Within the frantic dance at the system's core, two stars can be drawn so close that their mutual gravity becomes a destructive force. They begin to spiral inward, a death spiral measured in millennia. As they approach, their outer atmospheres tear away into a shared, chaotic shroud of plasma. The final merger is not a gentle collision, but a cataclysmic release of energy that outshines the other 5 stars combined, a temporary new sun blazing in the heart of the system. The aftermath of this stellar violence is a single, bizarre object, a blue straggler star. This is a cosmic Frankenstein's monster, a star that appears unnaturally young and blue. It was created by the fusion of 2 older, smaller stars, mixing their fresh hydrogen fuel in a new, more massive body. This new star burns hotter and brighter than either of its progenitors ever did, and it often spins at a ferocious rate, whipped into a frenzy by the angular momentum of the inward spiral. Its existence is a direct violation of the standard stellar life cycle, a celestial anomaly born purely from the chaotic, crowded conditions of the Septuple system. It is a permanent monument to a stellar marriage that ended not in divorce, but in a violent, brilliant union. That subtle wobble in a star's motion is more than just a gravitational signature, it is a potential message from a hidden world. Astronomers are now training their most precise instruments on these septuple systems, searching for the astrometric wobble that would reveal an orbiting planet. The principle is simple enough. A planet's gravity tugs on its host star, causing the star to trace a tiny circle in space as the planet goes around it. In a calm system like our own, this wobble is a clear, clean signal. But here, with 6 other suns constantly pulling and jostling the star, the signal is buried in a cacophony of gravitational noise. It is like trying to hear a single, quiet whisper in the middle of a roaring hurricane. The star is already being yanked in a dozen different directions by its stellar siblings, its path a complex braid of overlapping orbits. To find the minuscule wiggle caused by a single planet requires untangling this entire gravitational knot first. Astronomers must build a perfect mathematical model of all 7 stars, accounting for every pull, every tidal flex, every past interaction. Only when this model perfectly predicts the star's complex dance can they look for the tiny, rhythmic leftover, the residual wobble that points to an unseen planetary companion. Success in this monumental task would be one of the most profound discoveries in modern astronomy. It would prove that planet formation is not a delicate process requiring a quiet, orderly nursery. It is a universal force, a relentless drive of nature that can assemble worlds even in the most chaotic and violent environments imaginable. Finding a planet here would mean that life, if it can find a foothold, might be possible almost anywhere, even in a sky dominated by 7 suns. These 7 suns do more than just cast light, they forge invisible bullets of pure energy. The constant gale of stellar winds flowing from each star at millions of kilometers per hour creates a perpetual battlefield. Where these winds collide, they do not simply mix. They slam into each other with the force of countless atomic bombs, generating violent shock fronts that ripple through the system. These are not just waves of pressure, they are nature's most powerful particle accelerators. Within these chaotic fronts, charged particles like protons and electrons become trapped. They are whipped back and forth by the tangled magnetic fields, gaining a little more speed with each pass through the shockwave. Over time, they are accelerated to velocities approaching the speed of light, becoming cosmic rays. Once these particles break free from the system's gravitational grasp, they embark on an epic journey across the galaxy. They weave through magnetic fields for millions of years, their origin long forgotten. Some of these high-energy particles eventually rain down on Earth, peppering our atmosphere. This means the strange, chaotic dance of a septuple star system, happening in a distant corner of the galaxy, directly contributes to the faint background haze of radiation that has always been a part of our planet's environment. These stellar families are not just isolated curiosities, they are active factories, forging the very high-energy particles that silently zing through the space around us, connecting their violent beauty to our own quiet corner of the cosmos. The very idea of a stable, life-giving orbit shatters in a septuple system. A planet's potential for life depends on its distance from a star, that sweet spot we call the habitable zone where water can remain a liquid. But here, that zone is not a placid ring, it is a shimmering, chaotic ghost. With 7 suns in constant motion, their combined heat and light create a habitable region that is perpetually in flux. It breathes, expanding and contracting as stars swing close and then retreat on their long, elliptical paths. A world that enjoys temperate conditions for a few centuries might suddenly find itself plunged into a deep freeze as its primary star moves away, only to be roasted alive millennia later when a different stellar partner makes a close approach. The climate on such a world would be a geological roller coaster, a series of extreme and unpredictable shifts. Imagine an ice age that descends in a mere 1,000 years, followed by a global heat wave that vaporizes the polar caps. For life, especially complex life that requires eons of stable conditions to evolve, this presents an almost insurmountable challenge. How could a sophisticated ecosystem develop when the very foundation of its climate is being rewritten by the gravitational whims of 7 different suns? The search for life in such a system becomes a search for the ultimate survivor, an organism that could hibernate through deep freezes and withstand global floods, all while its sky is filled with the ever-shifting lights of its multiple parents. Sometimes the system itself becomes a telescope. The combined gravity of 7 suns warps the space around them so profoundly that it creates a natural lens, a shimmering distortion in the fabric of space-time. When a distant background star drifts into perfect alignment directly behind this septuple system, something extraordinary happens. The system's immense gravity bends the faint starlight, focusing it and causing the faraway star to temporarily flare in brightness. This is a gravitational microlensing event, a cosmic alignment of breathtaking precision and rarity. For a few days or weeks, that single, distant sun can shine hundreds of times brighter than normal, its light amplified by the invisible lens of the 7 suns in the foreground. These events are more than just a celestial curiosity, they are a powerful probe into the system's hidden architecture. The way the background star brightens, the specific shape of its light curve, tells a detailed story about the mass doing the lensing. A simple, smooth rise and fall would suggest the mass is evenly distributed, but the light curves from these events are never simple. They are spiked with complex bumps and secondary peaks. Each anomaly is a clue. A sharp, brief spike in the middle of the event could be the signature of a Jupiter-sized planet orbiting one of the stars, its tiny gravity adding a miniature lens of its own. A more prolonged wiggle might reveal the presence of a faint, failed star, a brown dwarf that had previously escaped detection. Most profoundly, a specific telltale distortion could be the fingerprint of the system's dark companion, the stellar mass black hole whose presence we've only inferred from the wobble of its bright siblings. In that magnified flash of a distant star, we receive a perfect, transient map of the entire system's mass, both seen and unseen. It is a fleeting chance to weigh the ghosts walking among the seven suns, using the universe's own natural lens to illuminate the darkness. This chaotic dance would sound like a symphony from another world. While space itself is a perfect vacuum, silent to our ears, the orbital motions of these seven stars create a complex rhythm of gravitational forces. If we could translate their precise orbital frequencies into sound waves, the result would not be a gentle melody. It would be a jarring, dissonant chord, a cacophony of overlapping tones that clash and resolve in unpredictable ways. This is the sound of chaos itself. Scientists are now using a technique called sonification to listen to this celestial music. They take the exact orbital data, the speeds, the distances, and the rhythmic eclipses, and they assign a specific pitch to each star's motion. The frantic, high-pitched whine of a close binary pair might be layered over the deep, slow bass note of a wide tertiary orbit. When these sounds are played together, our ears can sometimes detect patterns that our eyes miss in a graph or a dataset. A brief moment of harmony in the noise might reveal a hidden gravitational resonance, a stable relationship between the orbits that allows the entire system to hold itself together. It is like trying to listen to a complex piece of modern classical music. At first, it just sounds like noise, but as you listen more closely, you begin to pick out the individual instruments and understand the composer's strange mathematical logic. By listening to the music of the spheres, we are not just creating art. We are using a new sense to probe the deepest secrets of this gravitational family, searching for the hidden rhythms that keep seven suns waltzing together through the void. These stellar families are more than just cosmic oddities, they are time capsules. The unique chemical fingerprint of a septuple system, the precise mix of elements found in its stars, acts as a permanent record of its birthplace. Every giant molecular cloud in the galaxy, every vast nursery of gas and dust has its own distinct chemical signature. It is shaped by the history of that particular region, enriched by the deaths of generations of stars that lived and died there long before. When a septuple system forms, it locks that specific chemical recipe into all seven of its suns. This makes these systems the ultimate tools for galactic archaeology, a way to dig into the deepest layers of our galaxy's history. By reading the chemical barcode of a septuple system today, astronomers can trace its origin back to a single, specific cloud that existed perhaps 10 billion years ago. They can determine if it was born in a quiet, suburban region of the Milky Way's disk or in a violent, star-forming frenzy near the galactic center. The system's current location is almost irrelevant. It carries the indelible stamp of its homeland. This is how we know that some of these families are true galactic travelers, systems that have migrated vast distances from their original nest. Their chemistry does not match the local stars around them, telling a story of a long and winding journey across the cosmos. These seven suns bound together are like a living fossil. They preserve a sample of the galaxy as it was in its youth, a pristine snapshot of conditions in the early Milky Way, allowing us to hold a piece of our cosmic past in the light of their present-day dance. For centuries, this brilliant point of light was catalogued as a single, unremarkable star. Its faint fuzziness was attributed to atmospheric distortion or simple imperfections in our early lenses. It was a cosmic secret hiding in plain sight, a family of 7 suns masquerading as one. The truth only emerged when we learned to combine the light from multiple telescopes separated by vast distances, a technique called interferometry that creates a virtual eye as wide as a continent. This, coupled with the crystal-clear vision of telescopes above our shimmering atmosphere, finally peeled back the layers of that distant light. The fuzzy point resolved not into one star, but into a tight-knit family of 7, their individual identities revealed at last. This revelation forces a humbling question upon us. Our stellar catalogues are filled with millions of similar, slightly ambiguous points of light. If one of them turned out to be a septuple system, how many others are also elaborate deceptions? How many more of these complex gravitational families are we still misinterpreting as simple, solitary suns? Every faint, unresolved speck in our sky now holds the potential for a similar secret, a hidden chaos of 7 suns waiting for our technology and our curiosity to finally unveil them. A world heated from within could thrive even in the most chaotic sky. Consider a gas giant planet that has found a stable orbit within the Septuple system, a colossal jewel with its own collection of orbiting moons. These moons would endure a gravitational assault unlike anything in our solar system. The relentless, shifting pull from not one, but 7 different suns would constantly knead and flex their rocky or icy interiors. This process, tidal heating, would generate immense internal friction, turning the moon itself into a furnace. An icy moon, a frozen world like Jupiter's Europa, would not remain solid for long. The intense tidal forces would melt its entire subsurface into a global, warm ocean, a hidden sea deeper than all of Earth's oceans combined, sloshing beneath a cracked, icy shell. For a rocky moon, the effect would be even more extreme. The tidal stretching could liquefy its entire crust, creating a global magma ocean, a perpetual volcanic hellscape glowing with the heat of its own internal torment. This bizarre source of energy presents a stunning possibility. Life in our solar system might huddle around the weak warmth of a distant sun, or hibernate in the dark, tidally heated oceans of an icy moon. But here, in the Septuple system, these 2 paths could merge in the most unexpected way. A moon orbiting a gas giant could be so far from the central stars that its surface is a permanent, deep frozen wasteland. Yet beneath the ice, a vast, liquid ocean could be teeming with heat and chemistry, all generated by the chaotic dance of 7 suns in the sky above. The very forces that should tear worlds apart could, in a perfect balance, become the engine that makes them live. The most likely place for life in this entire chaotic family might not be a planet basking in the light of its suns, but a frozen moon, warmed from the inside out by the silent, relentless gravity of its 7 parents. The stars themselves are spinning at odd angles, tilted against the plane of their own grand orbital dance. We can measure the axis around which a star rotates, and in many septuple systems, this spin is wildly misaligned. It is not a simple, orderly rotation like a marble rolling along a groove. Instead, these suns are rolling, tumbling through their orbits like a collection of spinning tops that have been knocked askew. This profound misalignment is a fossilized record of past violence. For a star to be tilted so dramatically, something must have delivered a powerful gravitational blow, a torque strong enough to wrench its entire orientation away from the original plane of the system. The most likely culprit is a long-forgotten close encounter. Billions of years ago, this septuple family may have swung perilously close to another massive star cluster or a solitary stellar giant. The gravitational pull from this passing intruder would have been immense, acting like an invisible hand that reached into the system and gave its members a sharp collective shove. The entire architecture of the dance was permanently altered. leaving the stars spinning on their new, tilted axes as the only evidence of that ancient interaction. Another, even more dramatic, possibility involves the system itself consuming a rogue star. A solitary sun wandering through the galactic void could have been captured by the Septuple's gravity. But this was not a gentle capture. The intruder would have plunged through the system, its gravity creating chaos, violently scattering the original members before finally being absorbed into the dance. The gravitational shockwaves from this event would have been enough to tilt the spins of every star it passed, leaving behind a family that is forever off-kilter. This stellar spin-orbit misalignment is a permanent scar. It tells us that the serene, balanced dance we see today is not the original choreography. It is a hard-won stability, a peace treaty signed after a cosmic battle that left every star spinning with the memory of that primordial collision. That final, silent dance will be the system's true legacy. After billions of years of shining, the seven suns will finally exhaust their nuclear fuel. Their brilliant light will fade, leaving behind a collection of stellar ghosts. The bloated giants will collapse into dense white dwarfs, spheres of crystallized carbon no larger than a planet. The most massive stars will have already exploded, their cores crushed into city-sized neutron stars or, for the very heaviest, collapsed into the absolute darkness of stellar mass black holes. The Septuple system will remain, but it will be transformed into a cosmic graveyard, a dance of dark, compact objects. Their gravitational bonds will hold, but the music of their motion will change forever. With no light to illuminate them, their waltz will be tracked by the ripples they create in spacetime itself. The slow, steady emission of gravitational waves will begin to drain their orbital energy. Over eons, this loss will be imperceptible, but its effect is relentless. The orbits will tighten. Stars that once maintained a safe, respectful distance will be drawn into an ever more intimate and fatal spiral. A pair of white dwarfs might be the first to merge. Drawn together over billions of years, they would finally collide in a titanic explosion, a supernova that could briefly outshine an entire galaxy. This event would send a powerful, low-frequency gravitational wave chirp echoing across the universe, a signal announcing the death of a binary pair. The surviving members of the family would feel the shock, their own orbits jolted by the sudden loss of mass, but their own fate is already sealed. A neutron star and a black hole might be the next to succumb. Their final inspiral would be a more violent affair. The neutron star, a perfect sphere of nuclear matter, would be stretched into a teardrop by the black hole's immense gravity before being shredded into a glittering stream of ultra-dense debris. As this material spirals into the black hole's event horizon, it could unleash a brilliant flash of gamma rays, a beacon visible across the cosmos. One by one, the dark partners will merge, each collision a spectacular finale that lights up the galaxy not with light, but with ripples in the fabric of reality. The Septuple system, born in chaos and sustained by a fragile balance for billions of years, will end its life in a final, catastrophic symphony of mergers, its story concluding with the most powerful signals the universe can produce. This flood of data is more than any single research team could ever hope to sift through. Every night, telescopes around the globe and in space capture the flickering light of these distant systems, generating a tidal wave of information that would take centuries for a small group of scientists to analyze. The sheer volume is staggering, a digital ocean of light curves and spectral readings. To navigate this deluge, astronomers have opened the doors to the world. They have created citizen science projects, online platforms where anyone with an internet connection can help unravel the mysteries of these seven-star families. Imagine a retired teacher in Tokyo, a college student in Brazil, and a night shift worker in Norway all logging on to the same website. They are presented with the same complex light curve from a distant Septuple system, a graph of its brightness over time that looks like a frantic, tangled scribble. Their task is a profoundly human one: to look for patterns. They might be asked to click on the points where one star eclipses another, or to flag a strange, sudden dip that doesn't fit the predicted rhythm. The human brain is exceptionally good at this kind of visual recognition, often spotting anomalies that a computer algorithm trained on expected patterns might miss entirely. It was a volunteer in one of these projects who first noticed the bizarre, synchronized flaring across 3 stars, a discovery that would have otherwise been buried in the noise. This means the next great revelation about septuple systems might not come from a PhD in an observatory, but from a curious individual simply exploring the data on their laptop. We are no longer just passive observers of the cosmos. We are becoming active participants in its exploration, a global community of detectives working together to decode the universe's most complex stellar families. These 7 star systems are the universe's ultimate examination for our deepest theories of gravity. Every complex orbit, every subtle wobble, and every timed eclipse within their chaotic dance is a data point in a cosmic experiment that has been running for billions of years, testing the very rules that govern matter, space, and time. For centuries, we have relied on 2 pillars of physics to explain the cosmos. Isaac Newton's laws of universal gravitation describe a force that acts instantaneously across vast distances, a cosmic tug of war that works perfectly for predicting the orbits of planets in our own solar system. Then came Albert Einstein, who reimagined gravity not as a force, but as the curvature of spacetime itself, a geometric warping caused by mass. His theory of general relativity has passed every test we have thrown at it, from the bending of starlight to the precise orbit of Mercury. But a septuple star system presents a challenge of a completely different magnitude. Here you have 7 massive objects, each one warping the space around it, all moving in a frantic, overlapping dance. The gravitational fields are not clean and simple. They are a constantly shifting, knotted web of spacetime curvature. This is an environment where the subtle differences between Newton's and Einstein's predictions are magnified to a level we can actually measure. For instance, Newtonian physics might predict the general shape of an orbit over a short period, but Einstein's theory adds tiny, extra corrections. It predicts that the point of closest approach for a star in a tight binary pair should slowly rotate around its companion, a phenomenon called periastron advance. In our solar system, this effect on Mercury is minute. In the intense gravity of a septuple's core, it can be 1,000 times stronger. By tracking these stars for decades, we are essentially watching a slow-motion movie of spacetime itself being stretched and twisted. If there is any tiny flaw in our theories, any minute deviation from what Einstein predicted, this is the laboratory where it will finally show itself. These systems push our understanding to the absolute limit. They ask a profound question: do the laws of gravity as we know them hold true in the most extreme gravitational environment we can observe? Or does the chaotic dance of 7 suns hide a whisper of new physics, a clue to a deeper theory that lies beyond Einstein, waiting to be discovered in the intricate rhythms of their ancient waltz? Our exploration of septuple systems inevitably pushes us toward a final, staggering question. If nature can build a stable family of 7 stars, what is the absolute limit? We are now actively hunting for the next tier of cosmic complexity, an octuple star system. The existence of 8 stars bound by gravity would rewrite our understanding of hierarchical stability. The delicate celestial nesting dolls of septuple systems already exist at the very edge of what our models predict can endure for billions of years. Adding an 8th massive body to that intricate gravitational dance introduces exponentially more variables, more points of potential catastrophic failure. The theoretical framework suggests that for an octuple to be stable, its architecture would have to be even more exquisitely layered than a septuple's. Perhaps it would consist of 2 separate, stable quadruple systems locked in a vast mutual orbit, a cosmic binary of binaries. Or it might be a septuple system that has managed to capture and bind a solitary interstellar vagabond, a stellar adoption on the grandest scale. The gravitational choreography required to keep 8 suns from tearing each other apart is almost beyond comprehension, yet our tools for the search are more powerful than ever. All sky surveys, like those conducted by the Gaia spacecraft, are meticulously mapping the positions and motions of billions of stars. Sophisticated algorithms are now scanning this immense dataset, not for single points of light, but for the subtle, telltale wobbles and complex rhythmic dimming that would betray a system of 8. They are looking for the ultimate gravitational signature, a pattern of motion so convoluted that it can only be explained by the presence of 8 distinct masses in a single coordinated dance. Finding such a system would be more than just adding another record to the astronomical books. It would force us to confront the true creative power of the universe, revealing that its ability to assemble order from chaos extends even further than we dared to dream. The discovery of an octuple system would stand as a monument to cosmic architecture, challenging us to find the new physical laws that allow such a magnificent and improbable family to exist. Our journey through 50 strange discoveries reveals a universe far wilder than we ever supposed. Septuple star systems shatter the tranquil image of a solitary sun and its orbiting worlds. They force us to abandon simple models and embrace a cosmos of dynamic, chaotic, and deeply interconnected families. These celestial marvels are more than just curiosities. They are the universe's ultimate natural laboratories, pushing the very laws of physics to their breaking point and demanding that our imaginations stretch to keep pace. They teach us that chaos and order are not opposites but partners in a delicate billion-year dance. So the next time you gaze up at the night sky, remember this. Hidden within the darkness between the familiar points of light are wonders beyond our wildest dreams, where 7 suns waltz in a silent, gravitational embrace. Keep looking up, stay curious, and join us as we continue to explore the deepest mysteries of the cosmos.